Hi, my name is Laura Marbella, and I'm excited to have this opportunity to tell you about some of the research we're doing in the Department of Chemical Engineering at Columbia University. Our research focuses on understanding and controlling processes that occur in devices that are used for electrochemical energy storage. We're all familiar with the lithium ion batteries that power our portable electronics, and we're starting to see electric vehicles take over an unprecedented share of the automobile industry. If we look to the future, batteries are going to continue to play an absolutely critical role in mitigating climate change by helping integrate renewables on the grid and enabling things like smart buildings. But in order to be able to do that, we need to be able to build better batteries. So, if we take a look at the energy density that we can achieve with a lithium ion battery today, we find that it's remained relatively unchanged for the past 30 years. And that's because the higher energy density technologies that I'm showing here all suffer from severe chemical and mechanical degradation during electrochemical cycling. So, to truly understand what's going on, it's helpful to take a look at what's going on inside of a battery. So, what I'm showing here is a cartoon of a lithium ion battery where we have the anode, the cathode, and these two components are separated by an ion conducting electrolyte in the center. Both the anode and the cathode have an interface with the electrolyte. During charge and discharge of the battery, the electrodes, the electrolyte, and these interfaces all undergo structural changes that are directly related to battery performance. And that is exactly what we are interested in characterizing in my group. So, in my group, we make all of our own batteries, we make our own electrode materials, and we do all of our own characterization. So, you get a wide range of expertise by being a member of the group. The main characterization tool that we use to look at these systems is NMR spectroscopy, although we do supplemental characterization with things like X-ray diffraction. But the one issue that we encounter when we look at batteries is that the phase transformations that occur in these systems are mostly amorphous. So, if we take a look at a battery during discharge and charge, and we try to identify the different intermediates that arise during these processes, what we see with X-ray diffraction is that we only see two crystalline phases, one at the beginning that's the pristine material and one at the end of discharge. However, if we take a look at the same material with NMR, what we see is a wide range of intermediates that are accessed during both the discharge and charge process. So we end up getting a much more comprehensive picture of what's going on inside of this material during our electrochemical discharge and charge event. So, just like organic chemists can use NMR to characterize material structure, we also use NMR to see what's happening inside of our batteries. In addition, because we're using a type of spectroscopy to look at what's going on inside of our system, we can also start to probe the dynamics in these materials. So, as you can see from this chart that I'm showing here, we can probe a wide range of kinetic processes in our sample, all the way from picoseconds to seconds, depending on what type of experiment that we do. So we can learn about a wide range of electrochemical kinetics. Another fun thing that we can do in these experiments is also introduce spatial resolution using MRI. So this is directly analogous to a clinical MRI. And what this allows us to do is look at the actual spatial distribution of different species in the battery and correlate this with our device performance. Because we're also able to do something like MRI, we can also do these in situ. So similar to a functional MRI, where a doctor may ask you to recall pain or happiness and see what areas of your brain light up, we can do the same thing with a battery. So what we can do with our batteries is apply a high current density and cause the cell to short circuit. And we can take an image of the exact structure that has caused that short circuiting event. Not only can we capture that structure, We can also take an image of that structure forming. So we have a direct link between our electrochemistry and the formation of the structure that has caused our degradation event. So that gives you a flavor of the type of research that we do in my group. We have a highly collaborative environment in our lab, as well as other groups at Columbia and external institutions. If you have any questions, please reach out to me or my graduate students, and I hope to see you in individual sessions on Friday. Thanks.